Alright, we'll look at lecture exercise 5 part C. So before that, shall we take a look at the structure of the starting materials and the product? So we'll just number the carbon. So I'll just put this as 1, 2, 3. So these are the main numberings I need to incorporate. 3. So if we just translate the numbering over to the starting material, you can see that we have 1 and 2 here. So there is actually an extra carbon number 3, because if you were to look at this particular portion, right? Shall we just number it as 4 and 5? You will notice that it actually matches one of your reagent, which is dimethylamine. Yeah, I think it's dimethylamine. Yep. So this is this particular reagent. So I just copy it over here. So I just number this as 4 and 5. Yes. Okay. So you realize that there's extra carbon which you need to get it from somewhere. And as I mentioned during the lecture, you have this HCHO. If you look up for it, it's actually formaldehyde. Yeah, the N at the bottom actually represent it to be in a polymeric form. As I mentioned during lecture, when you actually buy it, you don't really get it in. It's very difficult to have it in the pure form. Yeah, so you can actually read more about that. So normally for this particular reaction, if we want to elongate the carbon chain, normally we will try to introduce formaldehyde together with maybe a dipropylamide as a combination. Okay, so without without going to too much complicated details, I'll just go straight into how do we actually go about proposing the mechanism. So first of all, we look at the presence of hydrochloric acid. So normally the presence of hydrochloric acid, right, it actually helps to protonate. Okay, so the main role is actually to protonate your aldehyde. So upon protonation, the carbon over here, in this case, I think you should be able to tell that it's actually carbon number 3. The carbon will then be a better electron deficient site. So it make it more electron deficient. Yeah, so the protonation of the carbonyl oxygen will make the carbon more electron deficient and therefore more susceptible to nucleophilic attack by this dipropylamide, dimethylamine. Some of you might be wondering, why is there a need to actually perform this particular step? Well, there is a need because if you simply just look at this particular product, I mean, we just simply look at this product. We can't simply join carbon 2 and 3 without any electron-rich and electron-deficient sites, for that matter. So that means what I'm trying to say is you cannot just simply whack 2 and 3 and then expect the N to join the 3. So there must be a reasoning behind it. And normally we are aware. I mean, after working on H3 for some time, you will be aware that a carbonyl compound like this. Okay, I've just highlighted it. A carbonyl compound like this, right? In the presence of acids, it can potentially undergo tautomerization. So for example, this compound, if I just paste it over here. Okay, so in the presence of the acid, let me just paste the lone pair as well. In the presence of the acid, it can simply undergo some form of acid base reaction. Okay, so I'll just put the H here. Okay, just quick one. So just put the H here. Okay, and then just change the size as well to 8. Okay, yep, and put the H. Yep. Okay, so I just drawing the arrows. So it will simply undergo acid base neutralization, and of course we call this protonation. So this O will be protonated. So you're going to end up something like this. I'm just going to delete away the numbering and then simply just put in the charge. Yep. you're going to get something like that, and of course, you're going to have OH here. Okay, so with this, when it's in this particular format, if you recall what I mentioned from the tautomerization activity, you know that it will actually drive uh, the formation of the relevant tautomer, and then this is going to happen, and then it's going to lose an H plus, okay, and then in the process, then you are going to form this particular tautomer. Okay, so I'm just going to delete. Okay, yeah, good. You are just going to form this particular tautomer, and then you notice that when you form this particular tautomer, there exists lone pairs on the O here. Okay, so this particular carbon right at the end, for the convenience of numbering, this will be carbon number 2. It will be the electron-rich site where it will perform nucleophilic attack on the relevant electron-deficient carbons. Okay, and of course, the nucleophilic attack will be on carbon 3, and therefore we need to generate an electrophile between formaldehyde, like formaldehyde, and this particular amine. Okay, so without going through the protonation step again, so I'm just going to delete this. Okay, assuming that it's going to be protonated, which I've already showed you earlier on. Okay, so I'm just going to add H. Sometimes the program doesn't work as well. So okay, so the lone pair, okay, from the end is going to perform again a nucleophilic attack on the carbon, and then the pi bond will then break towards the OH. Okay, so this is going to happen in the first in this particular step. So I'm just going to show you how the nucleophile, how the electrophile, okay, is being generated in this case. Okay, so sorry, it might take a bit of time because I'm just going to draw it double quick time. Sorry, I think this might work a little bit better. Okay, so so this is the end here. Okay, and then once it performs a nucleophilic attack, it's going to have the OH here. Okay, so I'm just going to resize it. Okay, so this is what you're going to get, and of course not to forget your N is actually charged. Okay, with H here. Okay, so I'm going to resize it as well. Okay, and then of course not to forget your N should take on a plus charge. Okay, something along this line. Okay, then of course this particular species is not going to be stable, so it will kind of equilibrate. So going to equilibrate. So there should be some form of intramolecular proton transfer in this case. I think uh, you are probably not new to this because remember that in the lecture we mentioned that along the way that there could be some form of proton transfer between electron-rich sites. So in this case, this particular intramolecular proton transfer, you can either draw it stepwise or just in one step. So in this case, I'm just going to draw it in one step. Okay, proton transfer. So this particular proton transfer will actually shift the protons into the other OH. Okay, so I'm just going to draw a quick one. And, okay, something like that. Just delete the proton off, and then I'm just going to put a plus charge on the O, something like that. And then probably going to put the OH2 like this. Okay, and of course, remember that this NH sigma bond is now broken towards the end. So in this fashion, I'm actually generating a lone pair. Okay, and then I have a good leaving group, which is H2O. Yep. So in this case, this particular group is going to leave. So I'm just going to attack to form a pi bond, and then this group is going to leave. Yeah, this kind of format is actually quite common. You have a intramolecular proton transfer, and then the lone pair from the end comes in, and then you kick out water. So water will then leave, and then in this fashion, you're going to end up with a relatively decent electrophile. Okay, I'm just going to shift this down a little bit. Okay, you're going to end up with an electrophile that looks like this. So there's going to be a pi bond, and then of course, I'm going to paste the charge over, which look like this. Okay, so now if I'm going to do a numbering, right, it's going to be 4. This is going to be, oops, sorry, this is going to be 5, and 3 is actually here. Okay, I'm going to put it here, and then this is 3. And then I hope from now onwards you can see that I have an electron-rich species here. I'm going to just put it on the left hand side. Rich species at carbon number 2. I have an electron deficient species at carbon number 3, and this becomes the perfect match because rich will attack poor. So in this case, I'm going to expect the formation of this pi bond. Okay, and then a nucleophilic attack like this. Okay, I'm just going to draw it the other way around. Okay, nucleophilic attack at carbon number 3. Okay, this is a little bit ugly, so I'm just going to do a little bit of rotation. Sometimes it's a little bit difficult to draw the arrow nicely. Okay, freehand is always easier. Alright, okay, and then I'm going to break the pi bond like this. Okay, I hope you can see this. So this pretty much allows you to by and large generate the product. Okay, by and large, I mean it's not really the whole product. I'm just going to paste this down. Okay, so you're going to generate the product below. Okay, I'm just going to draw it below over here. Okay, and of course the only difference is that now my oxygen is going to be protonated, which is which is actually a small issue because remember that as much as possible, what we really want you guys to draw is to depict something as close to reality as possible. And if you want to draw your product out, you have to show the deprotonation like this. Okay, so I hope I have given you a relatively short summary on how you could go about proposing mechanism like this. So if you were to go back to do a little bit of summary, I think first of all we need to understand the nature of the reagents. So we have this particular reagent, which is known as acetophenone, and then we have formaldehyde, and then with this particular amine, and then eventually we're going to end up with this particular product. We need to join up carbon 2 and 3. In order to join up, we need to propose where is the electron rich and where is the electron deficient site. Okay, and of course you need to have a little bit of knowledge, for example, from tautomerization as well. You need to know where is your electron-rich carbon, which is likely to be carbon number 2. And if carbon number 2 is electron-rich carbon, you need to be able to show how in the presence of the acid you can actually make carbon number 2 an electron-rich site, because the OH lone pair will be the electron source. And then therefore I need to generate an electron deficient site at carbon number 3, and of course in the presence of acid I do expect a reaction between formaldehyde and dimethylamine, and then in the process I generate an electrophile. Of course now the electron sink is at the nitrogen, and then carbon 3 is the electron deficient site. Okay, so remember that when you push electron density, you push from the source for the OH lone pair, pi bond attack 3 into the sink, which is the nitrogen with the plus charge. Okay, so I hope this clarifies any of your doubts.